I want you to imagine, just for a second, an entity with absolute unmatched intelligence. I mean, it has ingested every textbook, every scientific journal, basically every piece of literature ever written.
Right, the ultimate brain in a jar.
Exactly. And, you ask it this incredibly complex geopolitical question, and it gives you this brilliant, historically grounded thesis.
Yeah.
But here is the catch. This entity has lived its entire existence inside a perfectly dark, silent sensory deprivation tank.
Oh, yeah, zero actual experience.
Right. So it understands the mathematical formula for gravity perfectly, but it has never actually dropped a coffee mug and watched it shatter. It has never, felt the physical resistance of pushing open a heavy door.
So it possesses this infinite semantic knowledge, but absolutely zero physical intuition. It's essentially just a disembodied brain processing statistical patterns of text.
Yeah, and let's unpack this, because that is exactly where artificial intelligence has been completely trapped.
Yeah.
But what happens when you finally drain that sensory deprivation tank? Like, what happens when you give that mathematical brain a pair of eyes, an intrinsic understanding of physics, and a real physical universe to actually interact with?
That is the big question right now.
Welcome to the Deep Dive. Today we are mapping out what is probably the most aggressive paradigm shift in AI since the transformer architecture. We are looking at the massive leap from AI that understands words to AI that understands worlds.
Yeah, we are officially crossing the threshold from raw language processing into native spatial and temporal intelligence. And, this is the foundational infrastructure for physical robotics and genuine digital twins. It's
So-
huge.
And you, listening to this, you're likely watching the rapid deployment of all these new models and maybe feeling a bit of fatigue, because despite this endless stream of increasingly clever chatbots, something fundamental has just felt absent.
Something's missing, yeah.
Right, because the underlying architecture hasn't been grounded in reality. But that changes with the emergence of large world models, or LWMs, and the dense mathematical frameworks powering them. Specifically, we're talking about 3D and 4D Gaussian Splatting, alongside enterprise physics simulators like NVIDIA's Omniverse. We are going to tear down the architecture of all of it today.
And to really understand the sheer magnitude of this shift, we have to look at Fei-Fei Li's pivot with World Labs. She recently delivered this really razor-sharp critique of the current LLM landscape, referring to these models as, quote, wordsmiths in the dark.
Man, that is such an incredibly potent phrase, wordsmiths in the dark.
It's perfect, right, because it cuts right to the core architectural limitation. A language model fundamentally is an autoregressive statistical engine. It just predicts token sequences.
Right, just guessing the next word.
Exactly. So it can write an evocative, structurally perfect poem about an apple falling from a tree, but it lacks any inherent grounding in geometry, in Newtonian physics, or in basic causality.
It doesn't actually comprehend why the apple accelerates.
No, not at all. It doesn't know how the apple occupies three-dimensional space, or, how photons actually scatter off its surface as it falls through time.
Which brings in this brilliant evolutionary biology analogy from the sources that I really want to dig into. We always try to establish the why before we tear into the how on this show.
Yeah.
And the biological why here tracks back about 500 million years to the Cambrian explosion.
Right. So if you analyze the evolutionary timeline, cognitive capability didn't just, scale linearly. It experienced a violent exponential leap.
Right.
And the prevailing evolutionary neurobiology theory points to the sudden development of vision coupled with autonomous movement in a physical environment.
Okay, so seeing and moving.
Exactly. The very moment an organism can perceive three-dimensional space and actively navigate it, its neural architecture is practically forced to develop complex spatial intelligence. Just to avoid being eaten.
Yeah, you have to process depth perception instantly. You have to calculate the trajectory of a predator, figure out your own physical bounding box, and decide, in a split second, if you can fit into a specific crevice to hide.
And that spatial scaffold forms the absolute bedrock of all higher-order intelligence. Human cognition, abstract reasoning, even mathematical topology, it all stems from our intrinsic spatial environment.
That makes a lot of sense.
Yeah. So Li's foundational thesis is that for artificial intelligence to break through its current plateau, just throwing more compute at text isn't going to be enough. The AI needs this exact same spatial grounding. It requires large world models.
And world model is a term that gets thrown around so loosely in the AI space right now. People use it to describe everything from like a chess engine to a new video generator. So let's establish a rigorous taxonomy here based on our sources. World Labs breaks the concept of a world model down into 3 distinct functional architectures. The first is what they call the renderer.
Right, the renderer. And this is basically where the entire generative video industry has been totally bottlenecked for the last couple of years. These are the models producing those viral, hyper-realistic video clips you see everywhere.
Oh, yeah. The ones that look like real life.
Yeah. They are highly optimized for human visual consumption. They generate stunning pixel arrays. But architecturally speaking, they are a facade.
They are the digital equivalent of a Hollywood backlot. You look at a generated video of a bustling Tokyo street, and from the locked camera angle, it's basically indistinguishable from reality.
Sure.
But if you were to somehow pause the video and try to walk behind a building, you'd find absolutely nothing there. It's just 2x4s holding up painted plywood.
That's spot on. Because the renderer lacks true geometric consistency. It possesses zero understanding of object permanence or spatial hierarchies.
Right.
The outputs look incredible from a predetermined trajectory, but the moment you demand arbitrary view synthesis-like, if you try to freely navigate that space, the latent space completely breaks down.
With it's just an image.
Exactly. The model hasn't calculated the back of the object, and it certainly isn't running an active physics simulation to determine how that object reacts to gravity or collisions.
Okay, so if the renderer is purely about this flat visual output, the second type in the taxonomy is coming from the polar opposite direction, right? The planner.
Right, so planners are purely utilitarian. They are optimized almost exclusively for robotics and autonomous agents. A planner basically takes a highly quantified current state of the world as an input matrix, and it outputs an action vector.
Can you translate that a bit?
Yeah, so it's calculating things like object A is at these exact XYZ coordinates. My robotic end effector is at these coordinates. Therefore, I need to adjust my servo motors by exactly this many radians to execute a grasp.
Okay, got it. Pure math and execution.
Yes. But planners have historically been completely devoid of any rich generative simulation. They're rigidly programmed for highly constrained environments. They don't imagine new physical spaces. They just execute mathematical optimizations based on incoming sensor data from the space they're already in.
Which brings us to the real convergence. The third type, and honestly the ultimate objective of this entire technological sprint we're seeing, the simulator.
The simulator is the linchpin. It is natively consumed by both humans and machines simultaneously.
Could break that down for us.
A true simulator fundamentally respects spatial structure, semantic hierarchies, and physics. It operates natively in 4D spacetime, so it can render photorealistic, ray-traced views that totally satisfy a human designer, right?
Right.
But while it's doing that, it's simultaneously exposing the rigorous mathematical colliders and physical properties that are required by a planner. So it's not just a video. It is a persistent, editable, interactive digital universe.
Now, I do have to play devil's advocate for just a second here. Because if I prompt a state-of-the-art video model to generate, say, a high-definition clip of an off-road truck driving over a rocky, uneven dirt road, and I watch the suspension realistically compress and rebound over every single rock. I mean, isn't that AI basically demonstrating an understanding of physics? It clearly learned the mechanics of a shock absorber, right?
Well, no. It learned the statistical distribution of what a shock absorber looks like across millions of 2D video frames.
Oh, I see.
It didn't actually learn what compression is. It is literally just pattern matching pixel arrangements over time.
Wow.
Think about it this way. If you took that exact same video generation model and prompted it with a counterfactual, say, now keep the exact same truck and road, but reduce the vehicle's mass by 80% and change the gravity to match the moon,
It would completely break.
it would hallucinate or just fail completely because it doesn't have an underlying physics engine calculating the interplay of mass, kinetic energy, and friction coefficients.
Here's where it gets really interesting because it's essentially the difference between memorization and comprehension. The video generator is like someone who has perfectly memorized a topographical map of a mountain range. They can draw it for you beautifully. But the simulator is someone who has actually hiked the mountain, felt the loose shale under their boots, and knows exactly how the wind shears across the ridge.
That is the absolute perfect distinction. And this exact lack of comprehension is what causes the infamous sim-to-real gap in robotics.
The sing-to-real gap. Talk about that.
So if you train a multi-million-dollar robotic system inside a simulation that only visually approximates reality, but kind of fudges the underlying physics, well, the moment you deploy that neural net into a physical chassis in a real warehouse, it catastrophically fails.
Because reality doesn't fudge the physics.
Exactly. It trips over a cable, it crushes a delicate object because its friction calculations were based on a visual approximation. So to close that sim-to-real gap, the training environment must be an uncompromising simulator.
All right, so the objective is crystal clear. We need to build large world model simulators. But to understand the mechanics of how these are actually being constructed right now, we have to look under the hood at the underlying mathematics. We have to rewind a bit to a massive breakthrough in 2020 that effectively ignited this whole modern era of spatial computing, the dawn of neural radiance fields, or NeurHefs.
Ah, yes, the Mildenhall paper from 2020. In the realm of 3D computer vision, it is honestly impossible to overstate the seismic impact of NeurFs. It fundamentally shattered the existing paradigms of how we represent 3D space inside a computer.
So let's strip this down to the studs. For decades, if you wanted to build a 3D environment, say a level in a video game or an architectural CAD model, you basically relied on discrete geometry.
Polygons.
Right, thousands of little triangles.
Exactly. You stitched together thousands or millions of tiny flat triangles to build a mesh, and then you wrapped a 2D image texture around that mesh. NeurFs completely abandoned polygons. They replaced discrete geometry with a neural network.
Specifically, they utilized a multi-layer perceptron, but they deployed it in a completely novel way. They weren't using the neural network to, classify an image or translate a block of text. They forcefully trained the network to memorize the continuous physics of light within a highly specific, bounded volume of space. And the architecture of how it actually queries that space is mind-bending. A NeurF takes a 5-dimensional coordinate as its input. Let's break those dimensions down for everyone.
Sure. So 3 of those dimensions are just your standard spatial coordinates, x, y, and z. A specific microscopic point in 3D space.
Got it.
The remaining 2 dimensions are the viewing direction, which are represented as angles, theta, and phi.
Okay, so it's not just asking where a point is.
Right. This means the neural network isn't just asked, what is at this location? It is asked, what does this specific location look like when I observe it from this exact angle?
And from those 5 inputs, the network computes and outputs just 2 tiny values, right? Volume density and view-dependent color. Volume density is essentially the network calculating, is there solid matter here, or is this just empty air?
Exactly.
And the color is the RGB value, but the crucial part, the really revolutionary part, is that the color is view-dependent.
And that view dependency is what made NeurFs look like absolute magic when they first dropped. Think about observing a polished metallic espresso machine. If you look at it from the left, you see the reflection of a window. If you move your head 2 inches to the right, that reflection naturally shifts across the curvature of the metal.
Just like in real life.
Right. And traditional polygon rendering struggles immensely with this. It requires incredibly expensive ray tracing or faked static environmental maps, but a NeurF handles it natively. The neural network essentially learned that if you query the XYZ coordinate of the espresso machine from angle A, the pixel is bright white. But if you query that exact same XYZ coordinate from angle B, the pixel is dark gray.
I used to think of a NeurF as a sort of AI magic 8-ball. Like you give it the coordinates, you shake it, and it magically tells you the exact color. But that analogy actually falls apart pretty quickly, doesn't it? Because a magic 8-ball implies randomness. A NeurF is a highly deterministic, insanely complex algebraic ledger.
Exactly. It's what we call an implicit representation. There are no actual objects stored in memory.
Wait, really?
Yeah. The espresso machine doesn't exist as a 3D model. It only exists as a probability distribution of light and density, totally baked into the millions of interconnected weights of that neural network.
And that mathematical density is exactly why early NeurFs were agonizingly, painfully slow.
Oh, incredibly slow. Consider the rendering process. To draw a single frame on your screen, the system casts a virtual ray from the camera lens through a pixel on your screen and out into the digital scene. Along that single ray, it might sample 100 different points.
Okay.
For every single point, it has to run a full forward pass through the entire neural network just to ask for the density and color.
And if you have a 4K monitor, I mean, that's over 8 million pixels.
Over 8 million rays times 100 points per ray. You are querying that neural network hundreds of millions of times just to render one single frame.
That is insane compute.
This is why early NERFs took days to train on a server farm, and rendering a single image took seconds. It was a mathematical marvel, absolutely, but practically useless for real-time applications like VR or robotics, which demand 60 to 90 frames per second.
Plus, because it's an implicit representation, this massive, totally opaque matrix of weights, you can't edit it. If there's a chair in the NERF that you want to just move to the other side of the room, you can't just click it and drag it.
Right, because the chair doesn't mathematically exist as a discrete object.
It's just a fog of weights. You would literally have to manipulate the training data and retrain the entire neural network from scratch for another 3 days just to move a chair.
Exactly. So NeurFs proved that neural rendering could achieve photorealism and perfect view dependency without polygons. But to build the persistent, editable simulators that Fei-Fei Li envisioned, the industry needed an exponential leap in speed and editability.
Which brings us to the breakthrough that completely rewired spatial computing. The 2023 paper from researchers at Korea, the quote-unquote JPEG moment for 3D generation, 3D Gaussian Splatting.
3DGS completely shifted the paradigm. It completely abandoned the implicit neural network approach of NeurFs during the rendering phase and pivoted to what we call an explicit volumetric representation.
Let's translate explicit representation into plain English for a second.
Explicit means the digital world is built out of distinct, mathematically defined, discrete elements. Elements that the computer can individually point to, store in memory, and physically manipulate. Instead of a black box equation representing a room, 3D Gaussian Splatting builds the room using millions of individual, semi-transparent, three-dimensional blobs.
I always picture it as a massive 3D pointillist painting. But instead of dots of paint, it's made of millions of microscopic, semi-transparent skittles just floating in space.
I love that analogy. The skittles are the Gaussians. And the sheer brilliance of the NVIDIA paper was how they defined the specific parameters of these Gaussians so that a standard GPU could process them with just terrifying efficiency.
Let's dissect the anatomy of a single splat, because this is quite literally the cellular biology of these new digital worlds. Every individual splat has 4 core parameters. First is position, its exact center point in XYZ space.
Right. Second, and mathematically the most critical, is the covariance matrix.
Okay, covariance matrix, what does that do?
This dictates the scale and rotation of the blob in 3D space. And crucially, these Gaussians are anisotropic.
Anisotropic. Let me just pause you there. What does anisotropic actually mean in this context?
It means they don't have to be perfect, uniform spheres. If you build a world out of perfect spheres, which are isotropic, you run into massive rendering issues.
Because they don't pack together perfectly.
Exactly. To create a flat wall, spheres either leave empty gaps between them or they overlap heavily, which creates a blurry, indistinct surface. Anisotropic means the covariance matrix allows the blob to stretch independently along different axes.
Oh, I see.
So a single Gaussian can compress into a flat, wide pancake to perfectly coat the surface of a table, or it can stretch into a long, thin needle to represent a single blade of grass or a strand of hair.
Okay, so we have position and we have shape via this anisotropic covariance matrix. The third parameter is opacity, right? Basically an alpha value determining how transparent the blob is.
Yep.
And finally, the color. But just like neuromaps, it's not a flat static color. The color is defined by spherical harmonics.
Spherical harmonics are just mathematically elegant. Think of them as a Fourier transform, but wrapped around the surface of a sphere instead of a 2D wave.
Okay.
They provide a standardized mathematical way to encode really complex directional lighting data. The lowest degree of spherical harmonics captures the base ambient color of the splat. But as you add higher degrees, you encode complex, view-dependent specular highlights.
The reflections.
Yes. So as the virtual camera moves around that single pancake-shaped Gaussian on the table, the mathematical function of the spherical harmonics shifts the color to replicate a reflection.
So we get all the breathtaking photorealistic lighting of a NERF, but without the crippling computational cost of running a neural network for every single pixel.
Exactly. Because once the system optimizes the position, shape, opacity, and spherical harmonics of these millions of splats, the actual rendering phase drops the neural network entirely. It uses an incredibly fast pipeline called differentiable rasterization.
I want to focus on that phrase for a second. Differentiable rasterization. Why does a typical GPU love this pipeline so much compared to a NERF?
Because modern GPUs are basically purpose-built to rasterize, to take 3D data and project it onto a 2D screen instantly. The 3D pipeline uses a highly optimized tile-based rasterizer. It divides your screen into a grid of 16 by 16 pixel tiles.
Okay.
It takes the millions of 3D Gaussians, mathematically squashes them flat onto your 2D viewing plane, and sorts them by depth from closest to furthest for every specific tile. Then it just runs a rapid alpha blending sequence from front to back.
Wow. So instead of casting millions of complex rays into a dense neural fog, it just sorts and blends a bunch of transparent skittles.
And because it leverages the highly parallel architecture of the GPU, it achieves this at 60, 100, sometimes at over 150 frames per second at full 4K resolution.
And beyond the speed, the explicit nature of 3DGS unlocks the holy grail of 3D generation, editability.
Huge.
Going back to our Skittles analogy, if you generate a room and there is a bizarre AI-hallucinated chair in the corner, you don't have to retrain a model. You literally just draw a bounding box around the specific cluster of Gaussians that make up the chair and you delete them. You literally sweep those specific Skittles out of the array.
You can delete them, you can translate their XYZ coordinates to move them across the room, or you can even duplicate them. You can grab a cluster of splats that form a pine tree, copy it 500 times, and populate an entire forest. 3DGS completely bridged the gap between generative AI photorealism and the granular control of traditional 3D graphics workflows.
Okay, so now we have achieved real-time, photorealistic, perfectly editable 3D environments. But if we go back to our primary goal of training physical robotics, a static room, no matter how beautiful it is essentially useless.
Right, the world isn't static.
The real world is not a frozen diorama. A robot needs to navigate moving crowds, predict the trajectory of a bouncing ball, or understand how fluid deforms when it's poured into a glass. To reach the simulator stage, the model must understand time.
Which naturally introduces the fourth dimension.
Right. Let's talk about 4D Gaussian splatting. When I first read the CVPR 2024 paper outlining how time was integrated into this ecosystem, my immediate assumption was just brute force. Like, I assumed that if 3DGS requires millions of Gaussians for a single room, then a 4D video must just generate millions of new Gaussians for every single frame.
A lot of people assume that.
But obviously that would melt even an enterprise server rack.
Yeah, storing unique 3D volumes at 60 frames a second would require terabytes of memory just for a short clip. It's impossible. The breakthrough in 4DGS was the implementation of deformation fields.
So how does a deformation field actually manipulate the space?
Instead of generating entirely new geometry for every frame, the architecture initializes a single foundational set of canonical 3D Gaussians. Think of this as the base layer. The rest stay to the scene.
The master set of Skittles.
Yes, the master set. And then it introduces a highly efficient, very lightweight neural network specifically designed to operate across the time domain. For any given timestamp, let's call it t, this neural network calculates the precise delta for each individual Gaussian.
Okay, what is the delta here?
It predicts how much its XYZ position shifts, how its covariance matrix rotates or stretches, and whether its opacity increases or decreases at that exact microsecond.
So this lightweight network effectively operates as a choreographer, just telling the canonical Gaussians how to dance and deform over time.
Exactly. And researchers have pushed this even further into native 4D primitives. In some advanced architectures, the Gaussian itself is anisotropic in 4 dimensions, x, y, z, and time. It is literally a space-time ellipsoid.
A space-time ellipsoid. That is staggering to visualize.
When the rendering engine needs to display frame 42, it mathematically slices a 3D cross-section out of that 4D hyperobject.
Okay, the math there is wild. But the practical output of this is what's being termed volumetric video. This isn't just a 3D space, it's a fully navigable 3D recording. You can walk around a fire pit while the flames flicker, or observe water splashing from completely free viewpoint trajectories, and it's all playing back in real time.
It's basically the closest technology we've ever developed to a true holodeck.
But I want to press you on the computational overhead for a second, specifically regarding highly dynamic events. In a volumetric video of an explosion, there are sparks and debris that exist for maybe 3 frames before vanishing. How does the system handle that temporal redundancy? Like, how does it mathematically decide what data to keep and what is just noise to throw away?
That is a great question. This is handled during the rigorous optimization phase of training, driven by gradient descent. The system is constantly evaluating a loss function, comparing the image it rendered against the actual ground truth data from the camera sensors.
Right.
And it continuously monitors the gradient of every single Gaussian.
So it's constantly auditing the performance of every single splat.
Precisely. If a specific Gaussian is only providing value, meaning It's only reducing the mathematical error of the image for a tiny fraction of a second. The system's adaptive density control recognizes that it is mathematically inefficient.
It's basically dead weight.
Right. The gradients will actively push the opacity parameter of that useless splat towards 0. Once its alpha value drops below a certain threshold, the system culls it entirely. It deletes it from memory.
Wow.
Conversely, in areas of immense high-frequency detail, like the chaotic surface of splashing water, the gradients will trigger the system to forcefully clone and split Gaussians to capture the complexity. It's this relentless Darwinian optimization process executed in minutes.
Okay, so we have the entire foundation now. We've moved from the slow neural fogs of NeurFs to explicit 3D splats to 4D deformation fields. We have the physics of light, space, and time solved at the microscopic level. Now let's step up to the macro level. Let's look at the commercial platforms actively synthesizing all this math into usable products.
This is where we return to World Labs and their flagship product, Marble.
Marble hit general availability in late 2025. It is positioned as a generative platform for creating persistent, spatially consistent 3D environments. But looking under the hood, Marble doesn't just output Gaussian splats. They pair the visual splats with what they call collision meshes. Explain why that pairing is the difference between a pretty picture and a functional tool.
A Gaussian splat, for all its stunning visual fidelity, is fundamentally a ghost. It's just a mathematical representation of light.
Right.
If you drop an AI-driven robot into a world made exclusively of splats and tell it to pick up a mug, its robotic hand will pass right through the table and the mug. There is zero physical resistance.
Because the computer only knows what color the object is, not its mass or rigidity.
Exactly. A true simulator requires rigid body dynamics. Marble solves this by generating a collision mesh, a highly optimized, invisible geometric shell that sits perfectly aligned with the visual Gaussian splats.
So it's 2 layers.
Yes. The splats handle the photorealistic ray tracing and reflections, while the mesh provides the hard mathematical boundaries for gravity, friction, and collisions.
And the input modalities for Marble are incredibly flexible. You can feed it a text prompt, you can give it a single 2D photograph, and have the multi-view diffusion models hallucinate the entire 3D room behind the camera, or you can even feed it panoramic video. But the feature that drastically alters the professional workflow is the chisel tool.
Oh, the chisel tool is the mechanism that finally brings rigorous engineering control to generative AI.
The documentation describes it as decoupling structure from style. I want to dig into that because generative AI has historically been a massive headache for professionals who actually need precision.
Absolutely. If you are an architect, generative AI has largely been a slot machine. You type modernist living room with floor-to-ceiling windows on the west wall into a diffusion model, and you pull the lever.
And you just hope for the best.
Right. The model might give you a breathtaking image, but the windows will be slightly off-center, the structural pillars will be mathematically unsound, and, a couch might be subtly fused into a coffee table. Diffusion models hallucinate beautifully, but they struggle immensely with hard spatial constraints.
Which is completely useless if you need to actually build the room in reality or simulate a robot navigating that specific floor plan.
The chisel tool bypasses this problem entirely. It allows a creator to build the underlying architecture using rigid, absolute constraints.
How does that work in practice?
So an architect can block out a room using plain, untextured gray polygons. They can say, this wall is exactly 4.2 meters long. This window cutout is perfectly centered. They establish the absolute truth of the geometry first. Then they apply the generative large world model over it as a stylistic layer.
Oh, so they could say, make this structural box a dilapidated cyberpunk kitchen.
Exactly. The AI is mathematically forced to respect the hard boundaries of the geometry, but it is given total freedom to hallucinate the neon lighting, the rusted metal textures, the Gaussian splatted reflections, and the environmental decay over those constraints. It transforms AI from a slot machine into a precision instrument.
Now, I want to clarify something about the user experience in Marble, specifically their click and expand feature, because it's very easy to misunderstand the latency here. The marketing implies you can endlessly explore a generated world. You walk to the edge of a generated forest, you click to expand, and you just keep walking. But a full generation in Marble takes roughly 5 minutes. So how is this actually functioning in practice?
It is really crucial to bifurcate the workflow into 2 distinct states here, the inference state and the generative state.
Walk me through the difference.
When you are inside the boundaries of a world that Marble has already finished generating, you are in the inference state. The GPU is just rendering the Gaussian splats and calculating the collision meshes. That happens instantaneously at 90 frames per second. It feels perfectly real and perfectly fluid.
But when you hit the boundary of that map and click expand,
Then you transition into the generative state. You are subtly asking the large world model to wake up, interpret the context of your current environment, hallucinate entirely new geometry, calculate the depth maps, run the diffusion processes to generate new textures, and optimize millions of new Gaussian splats to ensure spatial consistency with the area you just left.
that is an immensely compute-heavy pipeline.
Right. So you click expand, you'd essentially wait for 5 minutes while the server farm does the heavy lifting, and then the new sector unlocks for real-time inference.
Okay, that makes sense. The computation of physics-aware, high-fidelity 4D environments from scratch is naturally one of the most demanding tasks in computer science right now.
Yeah.
This is exactly why these platforms operate on strict API limits and heavy compute credit systems,
Yes.
which provides the perfect transition to the real apex of this technology. Marvel provides the generative stage and the prompts. But if you want to orchestrate a simulation of, say, 10,000 autonomous warehouse robots on that stage, training them via reinforcement learning, Marble's collision meshes alone aren't enough. You need an industrial-grade physics operating system. You need NVIDIA Omniverse.
Omniverse is the Leviathan here. NVIDIA has explicitly architected it to be the foundational operating system for the era of physical AI.
And the bedrock of Omniverse isn't even proprietary NVIDIA code, which is fascinating. It's built entirely on OpenUSD, Universal Scene Description.
Why does a scene description need to be universal, and why is this so critical to the whole architecture?
Well, historically, the 3D pipeline has been a fragmented proprietary disaster.
How so?
An automotive engineer designs a chassis in CAD software. The aerodynamicist tests it in a specialized fluid dynamics simulator. The marketing team animates the commercial in Maya. None of these file formats talk to each other. Exporting from one to another inherently degrades the data, strips out physics metadata, or breaks the textures. It's a massive friction point.
It's a nightmare. OpenUSD, which was originally pioneered by Pixar, isn't just a file format, it's a runtime database and a composition engine. It is the universal language of 3D data. It allows entirely different software ecosystems to non-destructively layer data onto a single asset.
So no exporting.
Right. The engineer, the physicist, and the animator can all work on the exact same OpenUSD asset simultaneously in real time without any data conversion.
An Omniverse is essentially a supercomputer operating system built to interpret and simulate OpenUSD scenes. The architecture here is deep. You have Nucleus, which acts as the real-time publish and subscribe database, syncing all this data. You have NUEC, the neural rendering engine that natively ingests the Gaussian splats we've been talking about. And then you have the engine that makes it all matter, the CSAT.
Physics is where Omniverse fully detaches from creative software and becomes an uncompromising engineering platform. PhysX leverages the thousands of parallel cores on NVIDIA GPUs to simulate reality at a granular level. It calculates rigid body dynamics, soft body deformations, fluid kinematics, electromagnetic fields, and hyper-accurate friction models.
And when you combine those perfect physics with this synthetic data engine called Replicator, the implications for robotics are staggering.
Replicator is arguably the most vital tool we have right now for closing the sim-to-real gap.
Give us an example of how that works.
If you are training the neural network of an autonomous vehicle, you cannot simply drive it on a physical test track and wait for it to encounter a child chasing a ball into the street at dusk during a rainstorm. The edge cases are too rare and way too dangerous to capture physically.
So you synthesize them.
You use Omniverse Replicator to procedurally generate that exact scenario, but you don't just generate it once. Through domain randomization, you generate 10 million permutations of that scenario.
Wow, 10 million.
You change the coefficient of friction on the asphalt, you alter the volumetric scattering of the headlights in the rain, you vary the mass and velocity of the bouncing ball.
And because it's running inside PhysX, the physics of the sliding car and the bouncing ball are perfectly mathematically accurate.
Exactly. You feed those tens of millions of synthetic, perfectly annotated scenarios into the autonomous vehicle's neural network. It learns how to react to a million crashes without a single piece of metal being bent in the real world.
And this pipeline culminates in Isaac Sim, which is Omniverse's specialized robotics framework. The enterprise adoption scale here is difficult to even conceptualize. BMW is utilizing this framework right now to construct digital twins of 31 entire automotive factories. Amazon Robotics is running Isaac Sim to optimize the swarm logic of 500,000 physical warehouse robots.
It's industrial scale.
They are simulating the entire supply chain, identifying bottlenecks, and achieving massive efficiency gains purely in the digital twin before they ever even pour the concrete for the actual physical building.
This is the realization of the entire pipeline. Let's synthesize the whole workflow we've discussed today. Imagine a robotics firm designing a new bipedal humanoid intended to perform complex disaster recovery. They need to train this robot to navigate collapsed buildings, unstable rubble, and totally unpredictable terrain. They obviously cannot physically build thousands of disaster zones.
So they start with World Labs.
Right. They prompt a large world model like Marble to instantly hallucinate 10,000 distinct, highly complex collapsed structures. Marble utilizes its multi-view diffusion to generate the layout, constructs the underlying collision meshes, and coats the entire scene in millions of explicit 3D Gaussian splats to make it visually indistinguishable from a real photograph.
And because it's outputting in OpenUSD, they just pipe those 10,000 worlds directly into Omniverse.
Seamlessly. Once inside Omniverse, the Isaac Sim framework applies the physics engine to those Marble-generated collision meshes. Now, the rubble isn't just a static obstacle. It has mass, it shifts under weight, it obeys gravity. The robotic neural network is dropped into these thousands of simulations. It utilizes reinforcement learning, attempting to walk over the rubble, falling, adjusting its servo parameters, and trying again.
It essentially trains for the equivalent of 100,000 human lifetimes inside this hyper-accelerated, perfect physics simulation.
And when you finally compile that optimized neural net and flash it into the silicon brain of the physical titanium robot,
It stands up, steps onto actual physical rubble, and it just balances. The sim-to-real gap is zero.
that is the ultimate promise of physical AI and spatial intelligence.
I do want to address a structural friction point between these ecosystems before we wrap up. Omniverse is fundamentally an enterprise-grade engineering environment. It requires deep technical expertise to configure the physics properties and manage the USD pipelines. Marble, on the other hand, really democratizes the world creation phase. Anyone who can articulate a text prompt can generate a structurally sound environment. Are we looking at a convergence where the generative creative LWMs fully absorb the rigid physics engines, or will they remain distinct entities?
I foresee them remaining architecturally distinct, but operating in a totally seamless symbiosis.
How so?
Marble acts as the imagination engine. It needs to remain fluid, highly generative, and capable of vast hallucination. Omniverse acts as the laws of physics. It must remain rigorous, mathematically absolute, and deterministic. You don't want a physics engine hallucinating gravity, and you certainly don't want a creative generator bogged down by calculating molecular tension. They serve two entirely different halves of the computational brain. The real innovation will be in the zero-latency data pipelines connecting them.
So what does this all mean for us? Let's zoom all the way out and look at the trajectory we've mapped today. We began with the realization that simply scaling text-based large language models will never produce physical intuition. They are, as Fei-Fei Li identified, brilliant minds trapped in a completely dark room.
Right, to give them sight and spatial awareness, the industry had to invent an entirely new mathematical language for rendering reality. We abandoned the slow, implicit matrices of NeurIFs and unlocked the blistering speed and editability of explicit 3D and 4D Gaussian splatting.
We figured out how to make millions of anisotropic skittles dance perfectly in 4 dimensions, and now we're watching the deployment phase. Platforms like Marble are allowing us to instantly hallucinate the geometry of new worlds, while NVIDIA Omniverse provides the uncompromising physics required to turn those worlds into hyper-accurate gymnasiums for artificial intelligence. We are literally constructing a parallel digital universe built on explicit mathematical splats designed specifically to incubate the neural networks of the machines that are about to enter our physical reality.
Which leaves us with a rather profound philosophical implication. We are currently pouring billions of dollars and unfathomable amounts of compute into engineering these flawless, Gaussian-splatted digital twins.
Oh, definitely.
Inside Omniverse, the physics are mathematically perfect. The lighting is perfectly calculated by spherical harmonics. The friction models are absolute. We are incubating these artificial minds in a synthetic reality that is, mathematically speaking, cleaner, more controllable, and vastly more perfect than the physical universe.
I see exactly where this is going.
When that deeply trained neural architecture is finally transferred out of the simulation and boots up inside a physical chassis for the very first time, when it takes its first step into our actual world, a world filled with uncalibrated lighting, degrading sensors, chaotic thermodynamics, and completely irrational human actors.
Yeah.
Will that machine's first genuine experience of reality essentially feel like a massive downgrade?
That is an incredibly haunting perspective. We are architecting a flawless digital heaven, solely to train machines to work in our unpredictable analog reality. That is a heavy concept to chew on. Thank you all for joining us on this deep dive. The paradigm is undeniably shifting from words to worlds. The underlying mathematics of our digital reality have been entirely rewritten, and the simulators are coming online. Keep your eyes open, because the future isn't just going to be written in text. It is going to be spatially generated. We'll catch you on the next deep dive.